right, thank you everyone for joining. I appreciate you taking the time today for joining us here at the workshop with the ARM Dev Summit. Excited to bring the Corellium team aboard on our workshop here. Tim and Rob, I'll let them introduce themselves in a little bit, but just to kind of give you a little bit of a heads up that if you're experiencing any audio issues or anything, you can use your phone to call in to the workshop. Numbers have been added to the chat. Today's presentation will be recorded, so if you get out of sync with things or if you need to go back and review things, rest assured you'll be able to have access to the recording and catch back up with things. We welcome your comments to speakers. Just make sure that you post anything to the chat box. We'll be monitoring those. If you have any questions about the code of contact, please see the FAQs there at the link provided there on the screen. And if for some reason the Zoom meeting ends prematurely, please try the link again in the ARM Dev Summit right away. If that doesn't work, wait 10 minutes and give us time to add the new link. But I think with everybody and given everybody that's in the room, I think we're in good shape there. So I'll be handing it over to Tim and Rob. They'll talk to them about themselves a little bit. And I'll just go ahead and stop sharing my screen. So Tim, you can take over and feel free to introduce yourselves and tell us a little bit about Corellium and what you're going to be doing here. Yeah, Tim, I'm not getting any audio from you.
Yep, that audio button hit itself, and there we go. Let me just pull up the slides again. Sorry about that. Awesome. So as you saw, we did have a quick little, tools to download, and I believe hopefully everyone in the class has already gotten an email invite, also an email from Rob that just mentioned where to download the slides so you can follow along at your own pace. I will be going through, and there are images for a few of the things that I'm going to try and do live, so you can see that at your own pace. As I switch between slides and the actual web app, because we're going to try and focus on using the web app to detail exactly the steps. And so hopefully you should be able to log into your account on the armworkshop.corellium.dev. And if you'd like to already pre-download the target binary, that'd also be a good thing to do. So thank you for joining us today for the ARM Dev Summit. It's a little early in the morning, potentially for some of you, might be late depending on your time zone. And just welcome to our talk, App Unknown, an introduction into rapid security analysis on ARM. So just a quick, who are we? We're both principal engineers at Corellium. I'm formerly did research for mobile security, worked on a couple security incident response teams, and I've also worked as a threat intel lead at a few small and large startups. My specialty is just reverse engineering, exploit research, malware research, and then lots of anti-everything kind of research, lots of stuff with Packers, obfuscation, and all that kind of junk. Rob comes from more of a hardware background, and he also is formerly of Qualcomm, and he specializes in software security countermeasures and tearing me apart on code reviews and whatnot, because he's a much better coder than I am. Where we're from and basically what we do there, we both work at Corellium. We specialize in mobile device virtualization. This is ideal for both application testing. So if you're a developer, it's very interesting, I think. It's also great if you do red teaming or auditing of applications and you want to tear applications apart. This is a great tool to be using for dynamic reverse engineering and just dynamic flowing. It's also just great for security research. So whether it's bug hunting in applications, in operating systems, or just researching basically an exploit payload you found or trying to create your own exploit payloads. The deep down nitty gritty of what makes our company really interesting is we call it CHARM. It's the Corellium Hypervisor for ARM. Essentially, this lets us, we like to call it like practice where you play. We basically get to run ARM on ARM. And so we're doing all the virtualization of ARM hardware, or excuse me, ARM bytecode back onto an ARM real bare metal device that's ARM. So essentially we can support AOSP, iOS, other Android devices. And for today, we're actually going to be running this on AWS Graviton. So when we run something that has ARM code, we're actually still running it underneath on an ARM processor. And this is different from other emulators, which tend to do translation, or they basically do, you can run ARM code, except you're going to be running that on an x86 processor. So that could either cause slowdowns or just sort of, miss some nuances or different errata and whatnot of what those bytecodes should be doing and versus what they actually are performing. So I kind of briefly just touched upon this, but essentially the alternatives to what we pitch and what we are using in this demo is, have a device farm. Potentially some of you folks have seen this. Lots of startups have these, lots of large companies have these. This image is an illustration of one that I've seen. Essentially, you're gonna have a big USB brick that you're gonna have to power and hopefully it doesn't fail. Then you buy countless versions of different phones or multiple versions of the same phone so that you can test an application over and over again, because you always want to have a singly reproducible environment. It's much better when you have VMs that are ephemeral, except you can't always do that. So what a lot of people have done is they've zip tied all these phones to different things, and that's just not great. Usually you need an army of interns or junior developers or someone people might care less about, but obviously we should respect all humans because these batteries sometimes explode, the screens sometimes break, the USB cables break, and it's just countless hours of debugging. I've had to help work set up some of these, and they're just not fun things to do, and they're very prone to having errors and issues, especially once you get to the scale of thousands of these machines that are just devices that are not meant to be powered on 24 hours a day, always plugged in, all that kind of fun and horrible stuff. It just makes scaling really hard. Another alternative to using VMs, and this is actually a slide from a different talk I've given that was called Android Fuzzanomics. Essentially, before Corellium existed and before I was able to get my hands on the product, a lot of things I would do would be, I'm gonna buy a cheap, like 32 core x86 machine because those aren't that expensive. And if I want to fuzz ARM code, I'm basically gonna take the C code that would be compiled normally to ARM, and I'm just gonna cross-compile that for x86. And usually that involves changing different system calls, different libraries, and hoping that doesn't change much, and then fuzzing. So then essentially you're able to fuzz extremely fast because it was an x86 machine with 32 cores versus a real device. But the issue you would have is you end up getting this huge swath of bugs, and it's sort of this funnel where you're coming down, you say, I have lots of bugs in x86. Will this reproduce in an emulator? I don't know. Will this reproduce in a real device? Sometimes it did, sometimes it didn't. Often I ran into issues where, well, the memory wasn't exactly aligned the way it would on a real device. So you kind of just waste a lot of time trying to find things fast on a faster machine, and then coming down to a real production device, and it just wasn't the same. So some bugs netted out to be good, some bugs netted out to be bad, but the point of it was, I wasn't practicing where I was playing, so you'd find lots of really interesting, fun stuff that ended up being useless on a real device. So again, these are the alternatives. They're definitely doable, but they all have their pros and cons. Just as a quick little overview of what we're going to be going through today. We're going to walk through dissecting an Android application. We're not actually going to statically dissect it or specifically reverse engineer it, but we're going to try and do this at a high level. So this should be viewed as sort of a speed run through understanding, is this bad? And I feel like that's something you might hear a lot if you're at a security department of like, how bad might this be? Is this bad at all? Can I get a sniff test? Something like that. And so we're just going to basically assume that you folks are generally technically savvy, but you may not actually have in-depth experience with reverse engineering. But hopefully we'll show you just some easy things that we can do to basically prove out whether something's malicious or not malicious. Also, these concepts are not specific to Corellium. We will be showing you, and we've given you access to Corellium. This is actually going to be the first time a lot of folks are going to be able to see the product. And this is going to be a newly launched product shortly, and it's running on AWS Graviton processors, which is really exciting for us. And so hopefully you'll be able to take a hands-on and actually enjoy using the product. But again, this isn't really supposed to be a product pitch because you could do all of these things outside of it. And we have definitely included instructions on how you could replicate this without using specifically our tools. Just to mention again, I don't expect everyone to be, a reverse engineering guru, or if you do, you might use different tools than I would use. So at some times this might seem like how to draw an owl, where we just go from, step 0, where I say, what's an owl? And then we go to 4, and all of a sudden we have this amazing photo. So please do ask questions, ask them in the Zoom chat. And at the end, we'll definitely be trying to stick around, and we do have a Slack that we can help you guys with as well. But for the most part, again, some things might skip over, or there might be little leaps of faith we have to take. But I would try and take this as this would be a team exercise if we were all on the security incident response team. And that's just sort of how security works, where each person on that team tends to be specialized or have different hunches. And so a lot of things that we might leap to would be maybe not one singular person working on this type of scenario. It might be, hey, I saw this, and I know, let's just say Rob is an expert at kernel things. So I'm not an expert at kernel things, but I can see it's doing something with a kernel. So I'm gonna kind of toss the ball over to him. So bear with us, and please feel free to ask any questions if we're going too fast or we may be misexplaining something. So the scenario we're gonna deal with today is something that maybe you guys have seen before. Maybe someone hasn't sent you exactly an APK file, which is an Android executable. But normally with today's day and age, everyone's been sort of been getting this drilled into their head that, even if someone and especially if someone you don't know, sends you an email, and that email says like, hey, click this, or it has a picture, or it has a link, or basically it's anything outside of text. Or if it's someone you don't know and it's text, it still could be bad because, essentially security has said everything could be bad at all times. So usually you get these training sessions that say, if any of those situations happen, which is pretty much every email you ever get, forward it to, security incident response @ or cert @ or security @ and essentially, what happens is we have, IT and security then starts drowning in, thousands of emails a day where everyone basically just forwards their inbox and essentially says, hey, is this bad? And it's like, no, that's from your manager. Yeah, that's bad. Okay, no, this isn't bad. But you end up just having this huge funnel of all these things that are almost always bad. So I would say at this time, if you haven't already downloaded the target application from the URL that's in the bottom right hand, and that we've already provided a few links to, please go ahead and do that. We'll be using that shortly. So now, essentially, if we were to start reverse engineering this, there's 2 different streams of reverse engineering that people tend to go with. And so there's usually static and there's dynamic reverse engineering. Static reverse engineering, very basically, that is essentially, it's akin to reviewing code in a text editor, though you don't tend to have the context of the surrounding libraries or the system that the application could be running in. So usually you're gonna pump this through a tool, and either that gives you something that looks like source code. In the case of Android applications, you can sort of decompile things into Java. It's not what the people actually wrote it in, but it will be similar to that. Or you could look at a disassembly file. And this is sort of, again, it's kind of Java-ish, but not really. So these are things that, they take time getting used to, understanding the nuances. How did the compiler actually compile the bytecode? So there's tends to be a steeper learning curve for these types of tools. They can be great. Generally, people think this is slower. This is usually more considered matter of fact, but it's not exactly one way that rules them all. The other approach is dynamic reverse engineering. You can think of this as sort of, it's like debugging a piece of code. So you might not be looking at all the source code at once, but you could attach debugger or you could attach specific tools, and you can kind of see what the flow of the execution is. So The issues with this are, usually you need a good environment that's set up that looks like the environment that potentially, malware might be targeting. Because if you make it too obvious that it's a fake environment, a lot of types of, I guess they would call them advanced, but most malware will just say like, hey, is this a real phone? If it's not a real phone, then why would I bother doing anything bad? And that's sort of the pitfall of dynamic reverse engineering is if you don't have a good environment and you can't coax the application into doing anything bad, then you can't actually prove that it did anything bad. And a great example of this would be on Google Play, they have the bouncer. And the bouncer was the public name for the system that they would run applications through to see if things were malicious. And then it became well known that they only ran it for something like 10 minutes. So all the malware authors would basically say, okay, don't do anything bad for 10 minutes. And then on the 11th minute, do something bad. So all the applications would get pumped through the system and they go, did anything bad happen? No. Okay, it must be good. And then they kind of just chunk it down the line. And then so if that was your dynamic reverse engineering session and nothing bad happened, you wouldn't see that it was bad. And then you might just think it's good because you didn't actually see any of the actual malicious behavior. So the two methods, again, are both equally good. It just depends for both your business or your personal acumen of what will give you the best return on investment. If you have a team that's huge and lots of people want to learn how to do reverse engineering, maybe some of them should learn how to statically reverse engineer things. If you have a lot of developers and you can instrument your own kind of VMs to actually detonate malware in, maybe you want to try and spin up some dynamic hardware where you can do taint analysis or any of that kind of stuff, but you're going to have to maintain that. So that's sort of where Corellium comes in this picture. Is we've basically built this system. It looks like a real device because it's basically a real device. So applications are going to run on it as if it's a real phone, and you're going to be able to do a lot of dynamic analysis and dynamic reverse engineering pretty easily. And that combined with a little bit of a learning of static tooling is pretty valuable. And then you don't actually have to maintain that type of environment because we're doing that for you. So again, all these different ways of approaching the problem are valid, but essentially, it's more of what is best for your company, your team, and what you would want to do. Pitfalls that you want to try and avoid, though, is don't sink too much time into maintaining something that's just going to be always changing, and don't rely on maybe one person to be able to do everything in case that one person goes away, whether it's different job or a different set of interests. You kind of shoot yourself in the foot if you're, putting too much time into either one system or relying on one human. Anyway, for this workshop, we're going to go the dynamic route because that's just built for speed, and we're going to be able to leverage our tool to do that. So at this point in time, if you guys can log in to your actual demo account that we've already sent you, and if you're going to have any trouble with that, please again ask in the Zoom channel, and we should have folks that should be able to help you with that. I see a message, but I'm going to let Rob handle most of those, and potentially Steve, who is also part of the Corellium team. So if anyone has any issues, please reach out to them. And again, we're just going to log into there. This next bit, oops, yep, there we go. The next bit is we're going to connect our VPN. This is somewhat optional. We can avoid doing this, but I do want to connect to one because I'm going to be doing some specific commands. A lot of things we're going to just be doing through the web UI, but essentially once you log into the web application and you click on the device, everyone should have one device in their project, and it should already be on and already set up for you. If you go to the Connect tab, there should be a Setup VPN. If you're on Linux, you're probably going to be using OpenVPN. That's what I'm going to demo in just one quick second. And essentially, you're just going to download that file, and you're just going to do sudo openvpn that file. If you're on Mac OS X, I think you're going to use something like TunnelBlick or TunnelBear potentially. But again, if you have any questions with that, please just ask in the Zoom chat, and people can help you. And again, don't worry, this is not super required, but it will be helpful for running a couple different commands. And I'm just going to skip forward to, this is what it will look like when you connect. And I'm actually going to download the profile myself and connect as well. So I'm clicking on the Connect tab, downloading the OpenVPN file. We see I have one, and it's default project, and it's number 1. And so I'm just going to pass it the good. Gotta love typing passwords during a demo. Cool, awesome. And so I am connected to the VPN, and that all looks good. And we can see my device. This is the actual device here. Again, this is where you can get your OpenVPN profile. And now back to the slides. Okay, so installing the target application. So we're gonna show 2 different ways to do this, and I'm just gonna give a little primer on it. If you're familiar with Android and doing Android tooling on whether it's Windows, Mac, or Linux, there's this tool called ADB. It stands for Android Debug Bridge. And what we can do is if we click that little button over there, that's that chain link thing. That's actually what is going to just copy that, and you'd be able to paste that in, and it will connect to the device. And just as a little call out, what this device IP address is, if we look down in the bottom, it's actually the services IP, and there is something called the Wi-Fi IP. And just as a little explanation for that, essentially, your local machine is connecting to the Corellium device, which is running on an AWS Graviton server. The VPN lets you connect over that services IP. That essentially lets us emulate, this is a USB connection that allows you to connect, again, for ADB. And we also have a console connection, which is just basically the D message that's being piped out. And there's other things that we can use this for that I'll be showing you later. And this is, again, that's the services IP. The Wi-Fi IP is a little different. That's the NATed device IP. It's used for inbound and outbound traffic to the internet. So the device actually only sees the Wi-Fi IP address. It's F0, I believe. So that's just a little explanation of why does this device have 2 IP addresses and why am I connecting to the service versus the Wi-Fi. It might be a little confusing, but this hopefully explains that. So again, if you are familiar with ADB, you can use this method where you're going to just do ADB connect to the device, to the service IP address, and then you could do ADB install. This traverses over the VPN. Again, it's simulating that USB connection. And essentially, it's the standard way that anyone is going to install anything on an Android device, assuming they have developer mode enabled, and they're trying to install something probably outside the Android market or the Google Play Store. I'm going to make it a little easier, and I'm just actually going to use the web app. And so I'm just going to switch back over to the actual demo screen. And someone holler if you can't actually see this. I believe I'm presenting my entire screen, so you should see my actual Chrome versus just the slides right now.
Yeah.
Anyway, I'm going to go to the, perfect, thank you. And so I'm going to go to the Applications tab. And what this is a nifty little feature that we have where it basically shows you all the applications that are installed. A lot of these are not, human accessible ones. It's different system applications, but it does show you what their icons are, what their size is, the type of them, all that kind of good stuff. But I'm going to go and click install. And I actually already have it pointing at where I downloaded my target application. So if I double click on that, we can see that it's uploading, it's installing, and now it's installed. We did see something pop over here. And so that was just a quick way to install it. I'm going to cheat a little bit because I do know what the name of it was. I believe in that email it was something like 2048, which is a game name. And so you can basically filter. And now we do see that this is the name, or basically the title of the application. And this is the package name. So, obviously that couldn't be bad because it's fake malicious. But essentially now we do see like we've installed this application. It was easy. We didn't have to use ADB. And that little trick I just did there, that is pulling the app drawer up. If you don't have an Android phone, this is, I think, equivalent on iOS of like swiping right, so you can see all your chiclets. But let's go back to the slides real quick now that we've installed the target application. Okay, I've already touched upon this. I'm just going to skim forward. So let's run the application and see what happens. And so if you haven't already connected to the display on my web app, I've already actually done that. So I could see the home screen. You're just going to click on that. This starts a Webrtc session, which is basically going to let you, see the desktop or the background or whatever that's called on an Android device. And now, so what we can do is we can either use the app tab that I was just on and click the launch button, or we could, now that we're at this screen, we can swipe up. So if you click on the bottom of the device and hold it and basically flick up, this is simulating you with your hand just kind of touching the bottom and flicking up. We would be able to get the app drawer, and we know the application name and which one just got installed, and it's 2048. And so if we can click that, let's just see what happens. And so I'm going to actually do that myself as well. And so I'm going to go over and do the flick up and 2048, and we see we got this nice little game. Awesome. I'm so glad that someone sent us this game. Anyway, we're gonna, this doesn't look inherently malicious, other than that package name's kind of weird. It just looks like a game. I still have no idea why anyone sent us this, but it didn't ransomware my device immediately. So let's just skip on to the next slide and see what we can do next. So when we're looking for malicious behavior, obviously all malicious behavior is not apparent to the user. A lot of people want to, either spy on you, steal your messages, steal secrets or something like that. So, when you're stealing things and it's supposed to be secretive, you usually don't just prompt them and be like, hey, hold on, I'm stealing all your stuff. So, you're going to present to maybe with the game or do stuff in the background. So one of the ways we're going to look for bad things is monitor the network traffic. There's multiple ways of doing this. One of the normal ways people go about this, and one of the ways people tended to in the past, would just be TCP dump. This lets you basically look at anything on one of the network interfaces, dump all the packets, and then you can analyze it in something like Wireshark or use CloudShark nowadays. This is great. It captures all the traffic, but it doesn't do any of the good things like decrypting the traffic. And that's important now that everyone uses, HTTPS, they use SSL, they use different types of encryption, and they use different kinds of certificates. So essentially, if anyone does anything over HTTPS, TCP dump is not going to see anything unless you instrument it a different way. There's other tools. There's man-in-the-middle proxy, SSL split. Those are similar, but they also kind of sit in between, and they lie to your device and they lie to the server on the other side. And essentially, if you're doing a HTTPS connection, I'm probably not going to say this technically correct, but essentially they'll take certificates, they generate certificates, they make the application think it's talking to the right server, and they sort of just forge everything in between. So your device thinks everything's okay, the server thinks everything's okay, but you're going to be able to steal all that encrypted traffic. And this isn't something that can normally be deployed against a normal device, but since we control this one, we can specifically tweak it and lie to it and tell it to accept things. There are ways to prevent this, and that's usually certificate pinning. And that means, an application is going to embed inside of itself basically the certificate that it would normally rely on the system to give it. And so by doing that, you can sort of say like, I don't even trust the system at all. And since I don't trust the system, I'm only going to trust what I know. And that is a little bit more difficult to get around, but it's only a little bit. Basically, you just get a reverse engineer or someone who knows how to use Frida to say, oh yeah, you want to know that certificate? Well, how about, take that one out and put this one in. How about that one? Just believe that that's right. Or they'll just hook a function that says like, was it the right certificate? And they just return something like, yes, that's the right certificate. Just as a quick little overview, TCP dump in our situation, this would be run on the device. So you're not actually running anything on your local machine. You would just run it there. We actually do have this tool pre-installed. It's helpful to see if traffic is flowing in certain directions, what kind of traffic's there. It's mostly helpful for non-encrypted traffic. And again, this is basically going to be, you can tap anything from the device to the internet. A little bit more complex is man-in-the-middle proxy. So this is, again, a very useful tool, but simplistically put, you're essentially making your local machine the man in the middle. So you're going to proxy all the traffic from the device to you. Then you go to the internet. Then you come back. and then you're basically decrypting what that server just said, and you're basically being able to ingest it, then you re-encrypt it, and then you send it to the device. And so the device shouldn't actually understand what's going on. The app probably doesn't understand what's going on, and the server doesn't really get it either. It just thinks you're talking to it. This is great, but it can be difficult to set up. I'm just going to skim over this. We did include how to set up man-in-the-middle proxy. This is marked optional. I'm not expecting you guys to do this, so I'm just going to skim over it really fast. Essentially, what man-in-the-middle proxy does is it generates a certificate. You're then going to forward to your host, like I just said in that diagram. You install a new certificate on the device, you then have to reboot the device, and you have to configure it. So what that looks like for the current iteration, for current Android phones, using the current man-in-the-middle proxies, you're going to have to do all this fun stuff and set up IP tables and do a bunch of stuff and set up the routes and make sure it's all good. And then I make a joke, this is a great tool. It's not the tool's fault, but since the operating systems change, since the devices change, since apps change, since man-in-the-middle proxy changes, basically you're gonna cry because this won't work probably right away. It'll work right this moment because we have tested this, but in a week when any of these things update, it might break, then you're gonna cry because you just spent 20 minutes debugging this, then you gotta go find the new tool, the new version, find the Stack Overflow message where someone else got the same error as you. Anyway, we're gonna skip that and we're gonna use the Corellium tool. We've modified Ssl Split so that it essentially sits between the device and the internet. And so you don't actually have to do anything really in particular. We've handled all that, all those extra steps where we do all the routing for you and we inject the certificate on the device so it doesn't even need to be rebooted. And this is gonna make it a little bit easier hopefully for us. So for now, let's transition over to the hands-on. And so for the hands-on, let's try and do some actual introspection on the traffic. I'm guessing there's just going to be HTTPS traffic. So we're going to use our Ssl Split Tool. And this is found under the Network tab. We're going to do start monitoring, and then we're going to kill the process that's currently running. And then we're going to run the application again and hopefully find some internet traffic. So I'm going to switch over to the actual browser again. And here we go. And so this might be a little confusing if you're not an Android user, since there's no real back button in most games, but there is we're simulating a back software button here on the left-hand side. If you click back twice, you'll see this toast emerge. It says press back again to exit. I've now closed the application. You could also use the kill button over here. That would also kill the process and that would stop it for you. But now I'm going to go to the Network tab and I'm going to click Start Monitoring. And so now I should be monitoring all the network traffic. And so if I go to the game and I run it, we now see some things pop up. And obviously this is a canned demo, and obviously I chose the most innocuous domain possible for this. But we do see that someone's reaching out to the host, malware.team. That seems weird to me. If we click on that, we can see some interesting things. They're going to the URL beacon. This was an accepted request. If we look in here, we can actually see that there's an authorization. So these are just like HTTP headers. These two stick out to me. They're non-standard. Okay, HTTP, that's a standard library that people are using in Android applications. So it's probably coming from this application. It's the only other application running here. We do see this authorization bit and something UUID, so unique user ID, something like that. As a response, we can see in here, these are just interesting bits. Okay, we see a JSON response, hey, welcome back. So maybe this device is connected before. I did run it before, so that's definitely a possibility. You might be seeing different things on yours, and I hope you're running through this demo right now. For the second request, what I do see here is I see payload. And so we do see that they're hitting this payload URI, and they're using something for that. We see that they're still using the authorization header. There was no UUID header here. And if we look at the response, you see, let's get a little bigger. This is interesting because we can see that they're dropping a file name that's called payload. And if you've ever done much reverse engineering or anything on Linux, ELF, that's probably an executable file. So it's the ELF executable file. That's what Android applications can also run under the hood. It's usually called like a native binary or something like that. But this seems suspect to me. So this does seem interesting. This doesn't seem like good behavior. You know, I wouldn't want to inject something just because they have the domain malware team, but all these things kind of seem really interesting to me right off the bat. Immediately, I'd toss some of this stuff over. I'd say like, okay, hey, where's my network guy? Where's my analyst? Can you guys dig up anything on this domain? Like, is this associated with any APT groups or any bad groups, or is this some weird game dev thinks it's funny to call their stuff malware.team because all my alarm bells are going off right now. Okay, so I'm going to switch back to the slides. I'm going to skip through these. These are just in case you want to reproduce this later or what you were seeing, but essentially it's just going through screenshots of what I just saw. Cool, so immediately we do see that there is beacon, payload, and there can potentially be a third one, but that step may have failed. So I'm just going to try and run this again and see if we get more activity in here. I'm not, so I may actually have a bug in my application. Anyway, if we go back to the slides. So what we do see is we did see the beacon, we did see the payload. It does look like it could potentially be an ELF binary payload. So it's interesting, it's suspect. You're not supposed to do that per the terms and conditions of what Google says. This is not a standard way of doing things unless, I don't know, you're a very popular game. Popular games tend to do quasi-questionable things like this. But we want to know what else is actually happening. Now that we've seen some traffic going to the internet and some things that may be suspect, let's see what's happening at the system level. So potentially if you're a developer and you've done anything on Linux systems, maybe you've had issues with an application that you've written and you've used something called strace. Strace essentially utilizes ptrace under the hood. And basically this is sort of like debugging, and it attaches to your process and it says like, hey, what kind of system calls are you doing and what are the arguments? And then it kind of gives you a nice little, well, it's not nice and it's not pretty, but it gives you the output and says like, hey, this thing didn't fopen, it did a write, it did a read, and this was the file descriptor it went to, and this is the data it did. So this is interesting, except malicious applications tend to try and detect this type of stuff. They detect if someone's attaching to them as a debugger. They try to do traps and like maybe they'll ptrace themselves, and this basically sort of gets around the ability to do that kind of work on that application. So it's a great tool, but it's a well-known vector for trying to inspect binaries. So a lot of things will try and get around that. And other things you can see it's talking to device nodes, file system. In Android, you can see if it's talking to the IPC layer. And then also you can see if it's doing any like network traffic type things. Enter core trace. This is a Corellium specific thing. We've implemented this in the hypervisor. It's a little complicated, but essentially the way you can think about it is if your device is here, the hypervisor is up here, and we've implemented it at that level. So the device doesn't even understand that this is happening. And so since the device doesn't understand it's happening, the applications cannot, in pretty much any fundamental way, very easily understand that that's happening. There are techniques that are relatively advanced, and people write papers on them, they get their PhDs on them, they're called red pills, stuff like that, and they're timing attacks. And so it is possible for you to detect that someone is doing this, but it's hard. And you need smart people to do it. And then usually what malware authors do is they wait for someone smarter than them to release it. Then they just take that, bundle it, and put it in. So unless someone specifically releases like a timing attack, especially for Corellium, it's probably going to be hard to detect this. It's not impossible, but it's much harder than just detecting like a ptrace. So again, this is potentially detectable, but it takes a lot of time and effort. So most adversaries just don't see it as a meaningful way to really try and stop being detected. They just don't really care that much. So let's do another hands-on. So hopefully, you know, we've seen the network traffic. We've definitely hopefully installed the application. And what we're going to do is we're going to run core trace against this and just see if we can find anything really simple, really interesting, just to sort of narrow down, like, is this application doing anything? And do we see anything that it's doing? So to do this, we tend to need to know what are the process names for an application. And this can be kind of wonky if you've never done any reverse engineering. So this is sort of going to be that take a leap of faith with me. And let's go ahead and do the actual practical part. So I'm going to switch over to my browser again, and I'm going to hop over to core trace. Now, just to show a little bit of what core trace can do, we can filter by different threads, and we can automatically add these here. And these are essentially as if you were going to run like the PS command. And there are a lot of processes. This is a fully functional device, so there are lots of things in here. Now, we did know that the package name had the word malicious in it. And so I do see that there is a process running or was running. It has its name kind of chunked off because that's the way that, you know, Linux is exposing the process name. But I'm actually not going to even filter by this. But if I wanted to, I could do something like name and then ui.malicious.app. And if I spelt it correctly and then added that, we would see something like this. And so we could filter based on, you know, a process or a PID of something that we already know. But right now, I'm just not even going to do any of those filtering. But I'm going to start tracing. And so what's going to happen is we're going to see that this will go up every once in a while. And the trace is running. So I'm going to run the application. And I'm going to, I don't know, click a little bit, do some things. I'm actually going to close out of it again. And I'm going to run it again. We do see that this is getting to be a large file. So I'm going to stop the trace. Trace is stopped. And so now what you would do is you would download this log. And this is going to be, again, this we only ran for maybe, I don't know, 10, 15 seconds, and it's quite a large file. But what we're going to do is we're going to download that. While that's downloading, I'm going to skip ahead to a few more slots. This is just what I've already showed you. And so what I'm going to do is I'm going to open up my terminal, switch over here, and my file downloaded as core trace. So I do see that. I see that it is the correct file. It's that size that I was looking for. And if I look into this file, we can see that, you know, this is a pretty busy text file, but it's showing me, you know, this is the time that it happened. This is, I believe, the kernel thread ID. This is going to be the name of the process. This is the process ID, so the PID. And then this is the function call that it called. And then we can see the arguments there. So there's a lot of data here. But what, you know, I will just say this is kind of like that pro tip is let's look for things that we've already seen before with the other tooling. And so I'm going to grep for malware.t. And let me just quote that because we know it was going out to that domain. So I want to see basically using that tidbit of information, how do I kind of like spiral backwards and find what process did that? What does the system think that process was? And ooh, I appear to have missed it. So I didn't catch it in that. Let me go back real quick. I may have killed the network. Let me stop monitoring. I do see that there. And let me clear this log. It's always nice when the demo gods don't play along. And so the log is cleared. I'm going to run trace again. I'm going to execute the application. Click a button. Sure, I'll start a new game. Close it out. Okay. Log got a little bit bigger this time. Maybe that's a good sign. And download. So now I have core trace 1. And so what I'm going to do is I'm going to do the same thing once that finishes downloading. And it has not finished downloading. So I'm just going to sit here and cross my fingers for this demo to go well. While I wait for that to finish downloading, this is what I was expecting to see. And so in this case, I would expect to see that there was a get address info on that. And that's essentially, I believe, one of the system calls where it's going to say like, hey, give me, this is writing over the socket actually. So it's a write system call and it's trying to get the information for this. So it probably is doing like a DNS lookup or something like that. Let's see if that finished downloading. It did. So let's see if I can find that. And for some reason, it thinks it's a binary file right now. Let me just see real quickly. That's interesting. Okay. For some reason, my system thinks that that is not a text file, even though it clearly is. So I do see, I see actually a couple times, so maybe I missed it on the first run while doing the trace, but I do see what that other slide was saying, where I do see the get address info for that. And the interesting part I want to call it here is that this was a write that was done by an async task. And we do see that it was a different process ID each time. So this is why it's sometimes kind of tricky to say like, oh, I just want to look at that package name, but it's not always the package name that's going to be doing the work. It looks like they've done it in asynchronous tasks that to kind of connect the dots for an Android application would be, hey, run this in the background so that you don't freeze my UI, and then you get one of those annoying little crash prompts on Android. So what I was going to do is I personally would start spiraling back here now that I know the process names that were doing what I think would be interesting. I would basically be grepping through and looking for async tasks. And so I'm going to do that, but at the same time, hopefully you guys were able to run that application again, rerun it, run that core trace, download the file. Hopefully you got it on the first try, unlike myself. And I do just kind of want to give you guys maybe a minute or two and see if anyone finds anything. If you find anything, feel free to unmute yourself or to just pipe it into the Zoom chat. I'm just curious if anyone finds anything other than that malware.team. Maybe if you look at that async thread, I'm going to try and look at those strings right now and see if I spot anything that's super interesting, but hopefully you guys are also doing this live as well. And I'll just sort of quickly skim through here. When we see something like this is doing some type of execution, this would be the actual, looks like it's executing this as a file. So that's sort of interesting. Also, just as a bit from before, we could have downloaded that actual file. If this was the payload that was actually being downloaded, we could basically replicate that curl request and grab the headers and basically send it off. And hopefully if the server is not trying to be too smart, we would be able to actually see what's happening there. Actually, yeah, this one's kind of interesting. They're running an executable file and they're passing an arg as a derp. So don't know what that is doing, but that's interesting. These are a lot of clues. So if you've ever wondered what the life of a security analyst is, it's actually grepping through a lot of text files. So it's very glamorous, and I'm surprised that they haven't put more of that in movies. Something that's interesting is maybe where you want to grep to see this package name and see if anything interesting pops up from there. And so this would be pretty much anything that includes that actual package name in there. So we do see, again, there's that file. This was that file being executed. We see lots of different things where they're doing things in that file directory. So has anyone found anything interesting or anything more interesting than executing payloads? Okay. Okay, well, at this time, I'm going to hand it over to Rob, and he's going to dive a bit further into this. And let me see if I can pass that baton and close this window. And it's all you, Rob.
Well, good morning, good afternoon. I think I'm going to demand a bit more participation from you all. I mean, can someone tell me like something that they're seeing in that trace that's interesting? So there's a comment in the Zoom chat in terms of getting the app running. If you click at the bottom of the screen and then the virtual screen and drag up, that should open the app drawer and your application should be there. You can also run it through the apps tab. If you find the app in the apps tab, there will be a launch button, which you can also click to run the application. That might be more user-friendly. And thanks for that command. So I guess to motivate the next section, if you look through that trace, you should find something exfil. This should be, I guess, toward the end. All right, so I guess I'm going to assume that you can see this in your trace. So when the application runs, you will notice that it attempts to read some files in the file system, and it attempts to set a system property that, both of these actions can only be taken by an application that's elevated its privileges. So from this, we can infer, that there is privilege escalation happening, which implies a kernel exploit of some kind.
Hey, Rob, could you share this? Yep, there you go.
So all right, we suspect a kernel vulnerability because the application is clearly elevating its privileges, and we discern this by looking at what it's doing. with some knowledge of the platform, you realize that it's doing things that would normally be prevented. If you are familiar with, or as your day job do C or C++ development, you're probably familiar with a tool called Address Sanitizer, or ASAN. It has a kernel space cousin called KSAN, and the two tools work very similarly. They're designed to detect dynamic memory errors, in particular out of bound and use after free bugs, and they're developer tools first and foremost. Like they're used in development, manual testing, and they're actually very, very effective. They're also useful in some cases for security analysis. When it can be used, it's a wonderful shortcut. It's appropriate when, if you're doing your work in a virtual environment, and this could be either Corellium or the Quick emulator, which is, I guess, the emulator that Google's virtual devices runs on top of. If the vulnerability that you're trying to analyze exists in the core kernel, so something like interprocess communication, like Binder, or memory management, like AshMem or Ion, these components will be present in virtual environments as well as on real devices. So if what you're analyzing happens to be in that part of the kernel, then it's appropriate to use a virtual environment for it, and you can apply KSAN. If you have a commercial product with an unlocked bootloader, you also have enough access to use KSAN. An example might be the Pixel line of devices. Motorola also has a good track record of releasing phones where you can unlock the bootloader. And sometimes for vendors that don't have such a great track record, you can source the phones from out of the country. So as an example, the Samsung Galaxy S9, if you purchase it in the United States, you're buying a version with Qualcomm Snapdragon chipset and the bootloader is locked. However, if you buy the same phone from South America, it has the same chipset, but the bootloader is unlocked. So, with a little bit of care, you can often find the device you're interested in with an unlocked bootloader. And then this would let you take the vendor's open source kernel, build it with KSAN, and then flash it onto the device. The third situation where KSAN might be appropriate is if you happen to work for a system on chip vendor like Qualcomm or Huawei, or an OEM like LG, Motorola, Samsung. In those cases, you're also going to have kind of sufficient access and technological expertise around you in order to use something like this. So before we use it, I'd like to talk about how it works. At a high level, it simply checks whether memory accesses are valid with compiler instrumentation. So it takes the pseudo code. We have a write on the left and a read on the right, and it will transform it during compilation to something that looks like that second block of code. If the access is unsafe, report an error. Otherwise, go ahead and perform the memory access. It should be clear that isSafe access is doing a lot of work. And the efficient implementation of that function is key to making these tools useful. And the kind of concept that works in ASAN and KSAN that lets them implement that function efficiently is called shadow memory. And it is essentially a giant lookup table. And it encodes the state of memory, whether it's allocated, unallocated, or a red zone, which I'll have a little bit more to say about in a moment. So to make this a little bit more clear, this is the memory layout of an ARM64 Linux kernel with 48-bit page tables. And you can see that the majority of the memory, or rather, a significant chunk of the memory is user space. And then this is followed by the kernel linear mapping of memory. And then after that, you have the KSAN shadow region. There's a compression factor with shadow memory. A single byte of shadow memory encodes 8 bytes of real memory. So 16 terabytes of the KSAN shadow region cover the 128 terabytes of the kernel logical memory map. And then you have the other half of shadow memory to kind of represent the remainder of the kernel. I guess to make things a little bit more clear, every time memory is allocated, we update the shadow memory with the state. So when we allocate a chunk in the heap, we will mark that memory as allocated. And then later when it's freed, we mark it as freed. When we access the memory, we perform a check. And this way, we can make sure that we're only accessing memory that has been allocated. So the pseudo code for the checks actually looks a bit more like this. First, we convert the address into the entry in the shadow memory table. Then we check if it's a safe access. If it isn't, we report an error. If it is, we continue with the access. There's a few other concepts here that make it more effective. One is red zones. A red zone is a region of memory that's allocated on either side of an allocation. So when a function is called and variables are set up on the stack, we put red zones between each variable. This way, if you have, say, an off by 1 error or a linear buffer overrun, it will be caught by a red zone. Because rather than clobbering another variable in memory next to your variable, we have these large regions, and any accesses to them we flag as a problem. It can also probabilistically catch more random errors. So if you have, for instance, code where the array index can be corrupted, that might end up writing almost anywhere in memory. Red zones can probabilistically catch that, but won't always catch that. Another technique that KSAN uses is called quarantining. This is where when we allocate a chunk of memory in the heap, we refrain from reallocating that chunk for as long as possible. And the idea is here, in a use after free situation, you have a dangling pointer that's still referring to an old chunk. And the longer that that chunk of memory is unallocated and marked as freed in the shadow memory, the better your chance of catching an access to that memory as a bug. Because if later on you recycle that chunk and you reallocate it, in the shadow memory, it's going to be marked as allocated. And even if you access it through the dangling pointer, KSAN will consider it to be a valid access. So it should be clear from this discussion that KSAN will not catch all bugs, but when it does catch a bug, it's a true positive. So it has false negatives, but it doesn't have false positives, which is, kind of, it's not perfect, but this is very good to have in a tool that, helps you verify that your code is running correctly. The other kind of aspect of the implementation I wanted to mention is the instrumentation can be inlined or outlined. And I think that's best illustrated with an example. I took a function here more or less at random from the kernel and disassembled it. And in the beginning of the function, there is a memory access. So the load register instruction kind of toward the middle of the listing. In outlined instrumentation, the compiler inserts a function call before all of the loads and stores in your program. And you can see that before the function call, we take the immediate 8, add it to the register x19, and save it in x0. And that is the argument that's passed to our function. And then if you look at the load register instruction, you can see that the immediate 8, the register x19, is the one that we load. Like that's the address that we load. So that's the one we check with ASAN. The advantage of outlining is it has a very minimal impact on code size. The kernel that we're using is about 13 megabytes. When you compile it with KSAN and outlined instrumentation, it increases in size to 21 megabytes. So it's still a huge size overhead, but it's much better than inlining. The downside is performance. With outlined instrumentation, it's going to mess with your caching because you have so many function calls to these ASAN functions. So they're going to kind of frequently in your cache and kicking out other things that should be there. The alternative to outline instrumentation is inline instrumentation. In this case, the function call is inlined into our assembly directly. So here in the memory to shadow memory function call, that needs to be as fast as possible. So if you want to check a particular address, you want to look up the state in the shadow memory as fast as possible. So the way that this is implemented, it's with an offset and a scale. If you look at the memory map, you'll see that the shadow region is at a fixed offset from the kernel logical memory map. So we're trying to check an address in the logical memory map. We simply have to add the offset between these two regions of memory and then scale it down 8 to 1 because the shadow region is smaller than the logical memory map. So here in the inline representation, this is where it applies the offset. This is where it applies the scale. This is where it loads from the shadow memory. And then the compare and branch not zero is the check. And that works because the encoding for fully allocated memory is 0. So if it's anything but 0, we need to do a longer check to see if it's partially allocated and may still be safe, or if it's memory that has been freed, or a red zone, in which case we found a bug. So inline instrumentation, that increases the size of the kernel from 13 megabytes to 28 megabytes. So massive size overhead, but it can be anywhere from like 1.1 to 2 times as fast as outline instrumentation. For manual analysis, the speed is not so much of a concern, but that would be a concern if you were fuzzing or trying to do kind of more automatic analysis. On a real device, the size is a concern because if you're going to build a custom kernel and then flash it, this has to go in your boot partition, and the boot partition may have limited size. So there may not be enough space for you to build a kernel with inline KSAN instrumentation and flash it on your device. In a virtual environment, though, this isn't a concern because space is effectively infinite. All right, so as an exercise, I'd like to run the application with a kernel that's compiled with KSAN. So on these slides, we go through the steps of running a custom kernel. You will go to settings, tap kernel, and then you see the component there that'll give you the option to browse to upload a kernel. Choose the kernel, and then once it's finished uploading, you'll see a check mark, then the name of the file, and then the save and reboot button will become blue and clickable. And when you reboot, you will be booted into a different kernel. So here we have links to, I guess, the kernel that you're currently using in the kernel with vulnerability tarball. And then there's the kernel with vulnerability and KSAN tarball, which has a kernel that includes KSAN. So I recommend that you just download the already built kernels. But for reference, we also have a link here to build instructions, which will work for both Corellium's kernel and also the quick emulator. So the emulator that's part of Android Studio, these same instructions will also work to build a kernel that should run in that environment. You know, so if you're interested, you can go through those steps, but you should end up with, you know, something like we have already built for you here. So, you know, please download the kernel. I guess go through those steps, these 3 steps here, to upload the image and reboot, and then run the target application. In the console tab, you will see the KSAN output. So I'm going to give you a few minutes to download, unpack the tarball, follow these steps, and then we'll talk through what you will have seen. So +1 to Silver Searcher, it is a neat tool. 8 bytes, I guess like that compression ratio of 8 to 1 isn't because it's a 64-bit machine. That's incidental. It's, I guess like 8 bytes is just however many bytes they could encode in a single byte of shadow memory, because they encode not just whether it's allocated, but they can also encode partial allocations. So like how many of those 8 bytes are allocated, as well as whether it's freed or a red zone. So I think if they had a more efficient encoding, like if that were possible, then the compression ratio would be more than 8 to 1. So it's kind of difficult to gauge where people are. If you could give me some indication, either over the mic or in the Zoom chat, if I've given you enough time to, all right, thank you, I appreciate that. And also, I mean, if you've been playing 2048 and want to tell me your score, I'm interested. You know, if you have any comments about things you've seen in the trace, would also be curious to hear. Just if you're using the command line. So I think I'm going to give another minute, and then I'm going to start speaking to the KSAN trace. That's a great question. I should have been clear about that. You want to upload the file called image. we'll talk about the other two files a little bit later, but the one you want to upload is the image. And sorry, I should have made that clear. So for the KSAN part, it won't be necessary to be on the VPN, in that, like you can see the output by looking at the console tab. But if you want to follow along with the section after that, then yeah, it's important to reconnect. All right, so I'm hoping at this point that you've had a chance to download it, extract it, upload the image and reboot, and hopefully running the application and then looking for the trace. In the interest of time, I'm going to keep going. So you can see the console tab up there. When you click that, after running the application, you should see a trace, something like this, in your console. So this, it turns out, is tremendously helpful. In that first line, KSAN is telling us that it's a use after free bug. And this essentially means that when KSAN detected an access to part of memory that wasn't allocated, it was in memory that had previously been freed. So that's how it can tell us that it's use after free. It can tell us in which function in the kernel this happened. It can also tell us whether it was a read or write access, how large it was, and the address that we were trying to read or write. It gives you the task name and the PID. Your task name will be different from mine. It should be something like payload followed by the beginning of UUID. And then we have three traces here. The first trace is, I guess, the call trace for the access where the memory corruption would have occurred if it had not been caught by KSAN. The second trace tells us when this chunk of memory was allocated, and the third trace tells us when it was freed. And looking at these traces, a few things are interesting. So in the trace for the allocation, you can see that one of the functions begins with the prefix capital S, lowercase y, capital S. In Linux, all of the system calls, their top-level handlers begin with this prefix. So when you see that, you know you're looking at a system call handler. In particular, this is the ePOL control system call. So the memory is allocated by that system call. If you look at the trace for the access at the top, you can see that it's actually the same system call, ePOL control, but it's following a different path. Instead of calling bind to poll and bind to get thread, we call EP remove and EP unregister poll wait. So if you go back to your core trace, you should be able to grep for ePOL control. One of the ePOL control results will be the system call that the application is using to allocate the memory. The other one will be the one that it's using to trigger the memory corruption. This is also telling us that its binder where the vulnerability lies, or at least its binder where we're allocating the memory. And if we look at the last trace where it's freed, we can see that it's an ioctl call on the binder device. So this also gives you kind of another touch point inside the core trace. You can look for open syscalls where they open the binder device node. And I guess this kind of lets you start building like a timeline in that you know that the memory was allocated in one task with epoch control, freed in the same task with an ioctl on binder, and then in a different thread, they do epoch control, this time to trigger the write. And if you're familiar with how use after free vulnerabilities are exploited, what's happening is because there is a software bug, there is more than one pointer to a particular chunk of memory. And when they free that memory, one of these pointers still exists. And what the attacker will do is, after they free that memory, they will do some series of system calls or some other approach in order to have the kernel reallocate that memory, but this time in a way where the attacker can control the values, so that when they, in that first call trace, they access that chunk of memory through the dangling pointer, it will treat that block of memory as if it were an instance of the previously freed chunk, when in actuality, it's attacker-controlled data. And this is how you kind of trick the kernel code into doing something that it would never normally do. So in the system call trace, between the ioctl that causes the free and the epoch control that triggers the write, you should also see a number of system calls in there, which will be how the exploit is massaging kernel memory to look the way it wants so it can get these memory corruptions. So I guess to kind of recap KSAN, when you can use it as an analysis tool, it gives you a lot of information very, very quickly, very, very high quality. If you worked for a vendor, you could approach a technology team with these traces, and this should be enough for them to kind of, properly identify and fix the vulnerability. If the vendor was, a third party, you could approach them with this and it would be enough for them to do something useful with it. So we only have a few minutes left, but there is one more thing that we wanted to talk about. At this point, we've learned quite a lot about our malware sample. Because the techniques we've been using so far are dynamic, we don't know for sure that it always behaves this way. In different environments, it may behave differently. But I guess, these are kind of the caveats of some of these dynamic techniques that we're using. But we have managed to learn an awful lot in a relatively short amount of time. With the next thing that we'll talk about, we're deviating a little bit from the theme of kind of rapidly gaining an idea of how things work. This is a tool for getting a much deeper understanding of what things are doing. And to motivate this, we know that in the function remove wait queue, the exploit is corrupting memory. And we may be interested in what does it corrupt. Based on the behavior of the malicious sample, we know that it's elevating privileges. If you take its behavior and you combine that with kind of an understanding of common exploit techniques, we already have a pretty good idea of what it's probably doing. So I guess for context and background, I just kind of briefly want to talk about some common targets of exploits. So like if you do have a way of tricking the kernel into writing to a particular part of memory, what sort of things might you want to change? So the first example is in Linux, there is mandatory access control called SE Linux, which lets you craft a policy where you can restrict threads the actions they can take on resources in the system. When done right, and you have like a nice narrow policy, this is an incredibly effective security measure. SE Linux can run in two modes, permissive or enforcing. In enforcing mode, SE Linux violations are fatal, and like they'll kill the program. Whereas in permissive mode, SE Linux violations are merely diagnostics. And permissive mode exists so you can run a program, see what it should be doing, and then craft a policy that will let it do all the things it should be doing. But it does also mean that in the kernel, there is a Boolean variable, SE Linux enforcing. And if this variable is false, and if there is no strict flag, then when the access vector check denied function is called, it will take a path through the function that doesn't result in an error code. So this has the effect of disabling SE Linux. So if you can write somewhere in kernel memory and you can overwrite this particular variable with 0, you disable SE Linux enforcing. There's a credential structure. Well, I guess stepping back. So in addition to mandatory access control, Linux also provides discretionary access control. And this is, I think, what most everyone is familiar with, like users, groups, and permissions, read, write, execute. I guess, data that the kernel uses to make these security decisions is stored in a struct cred. Every thread in user space has a corresponding struct cred in kernel space, which contains these values for that thread. So you can see in the slide the user IDs and group IDs. If this were a text editor and you could scroll down, you would also see the kernel capabilities are stored in the cred structure as well, which are yet another, I guess, type of access control that the Linux kernel provides you. So if you can overwrite these values with different values, say 0, which is the UID of the super user, that's one way to elevate your privileges. So I think in the interest of time, what might I do? All right, so I think what I want to say is it is possible to attach a debugger to the kernel. There's really nothing better when it comes to seeing what's happening because you can inspect all memory and you can do this instruction by instruction. The caveats are that it's difficult to set up, and more importantly, to make use of the data, you need to have a pretty good understanding of what the Linux kernel looks like in memory. I would recommend you to check out a tool called SystemTap. It is a dynamic instrumentation tool for the Linux kernel. It's more user-friendly than kernel debugging. So in most cases, you'll probably find it more useful to use SystemTap first and then kernel debugging second. Kernel debugging is easy in a virtual environment. All right. So I think what I'll do is, for the moment, conclude. And then Tim and I will kind of stick around, and if there's interest, we can go over the rest of the material and take questions and things like that.
All right. Thank you, Rob. Really good. Yeah, leave the context screen up there for a little bit. And if anybody has any questions, they can raise them now, either through the chat or you can unmute yourself. So feel free to do that. Just a reminder, this is being recorded, so you guys can take a look at things later on and all that. Give us a few hours. We've got some editing to do, but then shortly we should be posting the link to the recording in the web interface for the DevSummit.
So as Steve is mentioning in the Zoom chat, if you want to kind of keep talking about things afterward, hop into the Slack channel and
Yeah, thank you. Thank you for that. Well, Tim, Rob, thank you hugely for this, and wanted to just say appreciate you coming on board. This was kind of a last-minute workshop, and the Corellium team really stepped up, and we think we did a really great job. And I want to just say a huge thanks to you both for putting this together, and the rest of the Corellium team for backing this up. As we said, the session will be available. They provided links to the slides too within the chat, and we appreciate that very much. I guess if there's no further questions, we will close this session. And
right before you close it,
okay.
I'll just mention that we'll keep the cluster running for a little while. So if you kind of want to play, go for it. If you want to experiment with the malicious sample, that will only work on Android 10 because we introduced the vulnerability specifically to make it work. But feel free to create other devices and play around.
Well, thanks, Rob. Appreciate that. All righty. If there's no further questions, we will conclude. Again, thank you very much. And we'll stop the recording now.